Morning, everyone. How y'all doing? Any questions, concerns, etc. from you guys before we get started today? All right. I'll just pick up from last time then. The plan for today and for the rest of the week is still to continue on in chapter 10. Today we're going to look more at some specific mechanics of sound itself. Talk a little bit about light as well, just how the two are related and different. I plan to get through a certain number of concepts and a formula or two today, and then on Friday we'll practice all of that and move into exam territory. So to review what we did on Monday, we began talking about vibrations, wave, and sound. Began specifically with the definition of simple harmonic motion that kind of drives all waves and wave-type motion. Looked at wave amplitude, wavelength, and frequency, things like that. And as it specifically relates to wavelength and frequency, which we'll pick up with those two things today. A wave's wavelength is, again, its physical size, the distance that it travels as it goes through one full vibration. And its frequency is how many waves will pass every single second. We measure frequency in hertz. And those are the two things, frequency and wavelength, that kind of tie most directly into the pitch that humans hear for sound. Human sound perception is based primarily on two different things. That being first intensity, which correlates most directly to volume, and then separately frequency, which correlates to pitch. Today's going to kind of be mostly concept driven. We'll do some light math as we talk about the concepts, just the stuff that I want you guys to know and know about sound as it relates to your life. But there will be a little bit more math towards the end of today. First, just to bring up sound intensity, again, as it relates to volume. I mentioned on Monday that sound waves, all waves, technically, are just traveling energy, correct? And every single wave is energy traveling from point A to point B, and it just causes whatever it's traveling through to vibrate as the energy moves through it. Since sound wave is just traveling energy, what you perceive as volume depends on how much energy is entering your ear or your eye, if you're looking at light, every single moment. The more energy that enters your eardrum every second, the more it causes your eardrum to vibrate every second, and then you perceive that as louder. So energy correlates directly to intensity and volume. And something to note about sound waves, I'm about to show an image that kind of shows the sound wave and the air vibration coming off from a handgun being fired. So the image is just meant to show how the sound is traveling out from this event. And so this sphere represents the air disturbance echoing outward from the explosion. And the way that intensity and volume plays into this is when the event happens, a lot of energy is unleashed, right? There's literally an explosion going off in this guy's hand, and that is going to put a lot of energy into the air, and we hear that as sound. That's also why very energetic collisions tend to be louder, because they put more energy into the air. When the energy enters the air, it causes a literal ripple, because the air wants to move, so it's going to vibrate as the air travels through it once it has the energy. And that energy is going to be very highly concentrated near the source, but that ripple, kind of like when you throw a rock in the water and you see a ripple echo out, that literal ripple is going to echo out in 3D space, so it's not just a flat circle, it's a sphere that grows from the site. That sphere is going to expand and carry all that energy with it. And the further away you get from the source, the more spread out that energy is, right? Because the bigger the sphere gets, the bigger its surface area. And so say this put 1,000 joules of energy into the air, that 1,000 joules is very highly concentrated in a very small sphere right as the event takes place, but as time passes and the sphere gets bigger, that 100 joules is spread out across literally more air, across a bigger invisible spherical surface area. And since that energy is more spread out, the effect gets weaker. The energy is spread out over a bigger area, and so less energy ends up in any given specific spot as the bubble gets bigger. And as less energy is in each spot, that means less energy would enter your ear if you are further away from the site. So this is why sounds get quieter the further you are away from them. Literally, the energy in the air just disperses and less of it enters your ear. But they're very intense near the source. So, intensity is sort of part of how humans interpret sound for this reason. The other part of how humans tend to interpret sound ties into the frequency of the sound. We talked about how on Monday all waves have both a wavelength and a frequency. And for sound, frequency correlates to the pitch that you hear. High frequency is high pitch, low frequency is literally low pitch. And that means that the frequency determines the type of sound that you are hearing. We're going to now compare this information with a formula that we looked at on Monday, talking about the speed of sound and how it relates to wavelength. Because we mentioned that every single type of wave has a specific velocity based on what it's traveling through and what that wave type physically is. So sound waves, all sound waves, if we assume room temperature air, has a speed of 343 meters per second. And if that speed remains constant, every different frequency of sound you can hear must have a different corresponding wavelength, because all the velocities have to match. So two different sound waves, like say if you double the frequency, the second wave would have half the wavelength, so that frequency and wavelength still multiply to the same number. So every different frequency will have a different corresponding wavelength. We used this formula on Monday to examine the speed of sound in the standing waves I made up here, but now we're going to do it to look at how frequency and wavelength work for sound specifically. So same formula, wave velocity equals frequency times wavelength. We're going to find the wavelengths of three different frequencies of sound. And I picked these three frequencies for specific reasons. We're going to assume the speed of sound is 343. That's the most common speed of sound as long as the air is room temperature. And we're going to find the wavelengths for 20 hertz, 6.25 kilohertz, and 20 kilohertz. So, I'll give you guys a second while I talk a little bit more about what these wavelengths, to find these wavelengths. I picked these three frequencies for a reason. The first one, the 20 hertz, is the lowest pitch that humans can hear. And even then, it's still a struggle. Like most humans are technically able to hear 20 hertz, but you still might not consciously notice it. It'd be a very low background bass. 6.25 kilohertz is an average human speaking voice frequency. Human speaking voices tend to fluctuate between 2,000 hertz and like 13,000 hertz, just depending on the individual. And even then, one person's voice is literally never just one frequency. Because if you've ever listened to sound tests or done anything with music, you know that solid single frequencies are just tones and pitches. And the human voice is not just one tone or pitch. Even if you try to make one constant noise, it's still an accumulation of frequencies. No one human voice is ever one frequency. So you hear multiple frequencies at once when a person talks. This is just why I'm picking a sort of an average based on the extreme limits of human voice. And the last frequency is the highest frequency that any human is physically capable of hearing, 20 kilohertz. So, What do the wavelengths for these sorts of waves look like? What's the wavelength for 20 hertz? (17.15 meters). Very good. That would come out as meters because you would plug in a velocity of meters per second, and hertz is literally 1/seconds. So you end up with units of meters. 20 hertz sound has a wavelength of 17.15 meters. And that is again meters. So in feet, that would be something like about 55 feet. A 20 hertz sound wave is literally an air pressure wave 60 feet long striking you. These low tones, all low frequencies, are bass tones. So bass instruments usually have lower pitches than non-bass instruments. And you ever noticed how if a speaker has the bass cranked up real high, it kind of makes your chest thump and your teeth rattle? At least I get that. I have a sound sensitivity. That literally happens because low frequencies, bass tones, have comparatively small frequency and huge wavelength. 16 meters is a big wavelength. It's a big column of vibrating air literally striking you, and that's why it makes your chest thump. I can feel it in my lungs sometimes. So those bass tones have huge wavelengths, and that's why you can feel them. It's making a lot of air move, and that vibration transfers into your body and makes you shake. So that is why bass thumps. And in fact, bass can be kind of dangerous. 20 hertz is the lowest frequency humans can hear. Even then, it's still a struggle. Any sound lower than that, so this is lower than 20 hertz, is called infra sound. Infra as a prefix just means lower. So low sound that's too low for humans to hear. And 20 hertz sound already has a wavelength of like 60 feet. Lower than that, the wavelengths just get even bigger. And that means that they're moving more air, and therefore they are going to make your body rattle more than normal. And that's why infrasound can kill you. If your body is exposed to infrasound for too long, you will start to feel sick, and eventually it can rattle your insides so much that you stop being alive. And people have developed weapons taking advantage of this fact. And they're very dangerous because you can't hear infrasound. Again, the lowest frequency you hear is 20 hertz. If it sounds lower than that, you can't hear it. You only know it's there once it starts making you ill. Now, infrasound doesn't exist very strongly naturally, thankfully. There's not just infrasound around us all the time. You usually have to make it artificially, and you don't encounter it much, which is good because it's bad for you. But apparently some ghost hauntings have been attributed to infrasound because it does weird things to humans. If a building is just vibrating at a sub 20 hertz frequency, it makes you feel sick, which sometimes triggers ghost haunting sensations in your brain. So infrasound is ghosts sometimes. And moving on from that, fun fact. Next frequency is 6.25 kilohertz. What is the wavelength for that?
0.05488.
Very good. You notice that I gave you kilohertz, which you do have to convert to normal hertz first. So that gives you a very small wavelength. If you just plug in 6.25, you get about 55 meters, which is bigger and therefore incorrect. Yes, human speaking voice and other similar sounds you interact with have pretty small wavelengths, in all honesty. Like most sounds you hear in a day range from like 200 hertz at the lowest up to a max of like 10K hertz. So pretty wide band of frequencies, but the wavelengths start getting very small very fast. And this is what the human ear was designed for. Small wavelengths, medium frequencies that your ear is actually able to successfully process. If you crank it up to 20 kilohertz, then you get an even smaller wavelength of 17 centimeters. And that's the point where your ear just can't receive the information too much anymore. It's vibrating too fast for your body to physically be able to process it as sound. And thankfully, unlike how infrasound can make you sick, ultrasound, the term for sound higher than 20 kilohertz, has no effect on the human body. It's because the wavelength is so small, it doesn't do anything to you. It doesn't cause your body to shake. This wavelength is tiny, frequency is too big to hear, so you literally just don't notice it. And that's why this is the type of sound we shoot at babies. It doesn't interact with the human body other than just echoing off of it. So this is safe to view babies, and this will kill you. So keep that in mind. Ultrasound, good. Infrasound, bad. I'll also note that this technically is a frequency humans can hear, but most humans can't, because this is like the highest frequency that the most healthy, freshest newborn baby could hear. And that number goes down every second you're alive since then. Because every second after you are born, your cells are dividing and aging, and that number just drops. I'd wager that most of you guys can probably only hear like 16 kilohertz tops. Mine's even lower, because I'm older and my headphones are too loud. That kills your ears faster. But that's the range of human hearing, and those frequencies tie directly to wavelengths, and the different wavelengths have different effects when they strike you. Any questions on this information or its application? All right. A couple more things related to this real quick. To compare humans to canines briefly, the range of canine hearing is 40 hertz to 40,000 hertz. So there's, 40,000 hertz. So there's a band of 20,000 hertz higher than humans can hear that dogs can hear, and that's the range that dog whistles operate in. Dog whistles are set to like 30,000 hertz. You physically can't hear it, but the dogs can. Conversely though, what I find kind of interesting is that dog hearing starts after human hearing. So there's a 20 hertz band of low frequencies we can hear that they can't. So if you want to make a human whistle, set it to 30 hertz. I think cats have a similar hearing range. I'll also mention that the correlation between a frequency and a wavelength paired up is also true of light, because light is also a wave and light has a constant speed. So different frequencies of light also have matching wavelengths, like how frequencies of sound have paired matching wavelengths. If you were doing it with light though, you'd have to use the speed of light, which is 3 followed by 8 zeros, 300 million. It's literally 1 million times faster than sound most of the time. And so the pairing of wavelengths to frequencies gets even wackier for waves of this type. I've got here in the notes, and this is just kind of interesting. We're not going to have to do any math for, well, no, I asked one question about it in your homework. This is just kind of to demonstrate the ranges of wavelength and frequency pairs for the different colors of light humans can detect. Again, since the speed of light is just enormous, you end up getting really tiny wavelengths and really big frequencies. The wavelengths for light are like nanometers long, and the frequencies of light are terahertz. And because the waves are so different, that's why your body has 2 different sets of organs to detect them. I'll also point out that light is just one type of wave amongst a family. Every type of electromagnetic radiation is the same basic thing. The only difference between them is frequency and wavelength pair. Radio waves have big wavelength, low frequency. Gamma waves have small wavelength, big frequency. But yeah, gamma waves and radio waves, technically the same kind of thing. Your phone is irradiating you, just in a harmless way. Questions about any of that info before I move on to something related? So, I've just compared light and sound to each other, and so I find it important to bring up what sound physically is and how it is different to light. Whoops, sorry, wrong slide. Because all waves are just traveling energy. I've said that a few times at this point. All waves are traveling energy, so on some level, sound and light are technically the same thing. They are traveling energy, but how that energy travels is different. Different waves are made of different, well, they're still made of energy, but they act differently depending on a few qualifiers. We mentioned waves are traveling energy, but waves can have two different shapes to them. The two primary wave shapes are transverse, where a wave is shaking up and down while the energy travels side to side. I'll kind of demonstrate this again with the standing wave. Oh no, it came loose. This is a transverse wave because the string is vibrating up and down as the energy travels back and forth in the x-axis. The vibration is perpendicular to the axis of travel. Come on. Tune, dang it. That's visible. So note, this is a transverse wave. The physical medium shakes up and down, but the energy is traveling back and forth in the x-axis. The vibration is in the y-axis. The definition of a transverse wave is the vibration is perpendicular to the axis of travel. This is the shape of light. And it's also the shape we tend to think of for sound waves because it's just kind of easier. But we assign this shape to waves as a whole, right? Like if you think of a wave, you think of this kind of shape. It's just easier for humans to see and perceive this shape. But technically, light is this shape and sound isn't. Sound is the other shape called a longitudinal wave. And this type of wave, rather than shaking up and down while traveling left to right, shakes left to right while also traveling left to right. Longitudinal waves vibrate in the same axis as travel. And it might be a little hard to see here, but what a longitudinal wave does is as it vibrates in the same axis, it's basically a traveling little pressure compression. I have a spring I'm going to try to show this on. So I'm going to try to demonstrate. To try to create a longitudinal wave on a slinky, you'd want to grab a coil, pull it back, and then release it forwards. And now the energy travels left to right, but the slinky's also vibrating left to right. This is what sound does. When you speak and put energy into the air, you're basically making a little ripple. A ripple that moves forward while also traveling forward, like when you throw a rock in the water. And that ripple is literally a little pocket of high pressure, and that pressure zooms off until it hits something, shaking in the same axis as travel. So the shape of sound waves are longitudinal in nature. It's a pressure pulse forwards as it travels forwards. I'll kind of mention again, I'll show the expanding sphere wave from the hand explosion. This pressure wave is a ripple traveling out in all directions, and the ripple is vibrating in the same direction as travel. So that's one primary difference between light and sound. Light is transverse, sound is longitudinal. But besides the shape difference, they also have different physical structures. They are still both traveling energy, but that energy is represented in different ways. In addition to wave shape, categorizing waves differently between longitudinal and transverse, there is a separate classification system called wave structure. And the two different wave structures is a wave mechanical or electromagnetic. Mechanical waves require a physical medium for the wave to travel through. And we mentioned on Monday that the speed of a wave depends on the medium it's traveling through, right? Sound travels through the medium of air. This standing wave travels through the medium of rope. Earthquakes travel through the medium of earth. All mechanical waves, they're physical in nature, they're caused by physical vibrations. They require a medium to travel through. And this is why you can't hear in space. There's no air in space. There's no medium for the sound to travel through. You probably heard that in movies or NASA documentaries, maybe The Martian. No air in space, can't hear in space. There's no medium. This is directly contrasted to the other type of wave, the other structure of waves, electromagnetic. These don't require a medium, so they can travel through space. These don't need air, they don't need ground, they don't need water, they just go, regardless. And the only real type of electromagnetic waves is light and its family. Light is literally made out of an electromagnetic pulse vibrating transverse as it moves forward. It's literally electromagnetic radiation. And since it doesn't require a physical medium, it's just going to go indefinitely until it hits something. And that's why it can travel through space. We get light through space from the sun, but we don't get sound through space from the sun. Which is good, because if sound traveled through space, the sun would deafen us. There's a lot of, roaring fire on the surface of the sun. If we could hear that, it would be bad. So, different types of waves have both different shapes and different structures. Sound is categorized as longitudinal mechanical. It shakes parallel to travel and requires a medium. Light is transverse electromagnetic. It's made of an E field and an M field vibrating up and down perpendicular to forward travel. We're mostly going to focus on sound. I just wanted to show there are fundamental differences between the two, even though they both exhibit wave behaviors. And again, that's why you need different sets of organs to perceive them. Sound as a physical vibration needs your physical eardrum to vibrate. Light, on the other hand, requires the photosensitive cells inside your eyeball that can absorb and process electromagnetic radiation. And even then, there's a lot of different types of electromagnetic radiation, and your eye can only detect but some of them, which is good. If you could see radio waves, that'd be pretty crazy because they're literally everywhere. Every phone in the room is making them. I don't want to see them. So, sound and light have very different structures, and speed of light is incredibly fast, and since it doesn't require a medium, that speed's pretty consistent. Light is the top speed throughout the universe, and nothing really changes that meaningfully. Even if light enters a new medium, it's still going to zoom. And so as far as human perception goes, the speed of light doesn't really change. But since sound is mechanical and it requires a medium, the speed of sound does vary, oftentimes to pretty big extremes. So let's look at how to calculate speed of sound. Sound is mechanical, it requires a physical medium. We hear sound best through air. So this formula is designed to tell you the speed of sound in air based exclusively on the temperature of the air. Because the sound's current temperature, the air's current temperature does interfere with how fast the sound travels through it. In general, if you keep pressure constant, sound is slower in the cold and faster in the hot. I assume the hotter air molecules are moving around faster, therefore they kind of knock into the next one quicker to transfer the wave along. Whereas if they are colder, they're moving more slowly and it takes them slightly longer to hit the next molecule to transfer the sound through. And this formula, V equals 331 times the square root of current temperature over 273 will tell you the speed of sound in the current temperature of air. That 331 is based on the speed of sound at temperature freezing, literally 0 Celsius, and that's why in the formula it has the temperature of freezing in it, just in units of Kelvin. So this formula uses Kelvin. I don't think I've asked you for temperature at all this semester. It's the one formula that requires it in this class, and it uses units of Kelvin. So just keep that in mind. So this formula literally just takes the freezing speed of sound and adjusts it based on current temperature. So the 273 is, 0 Kelvin, sorry, not 0 Kelvin, freezing, 0 Celsius. And you take the current temperature in Kelvin and pop it there to figure out how much faster than that it's going. Just for context again, if you're in boiling air, which would be bad, the speed of sound would increase to 286. Now, let us apply that information to a couple different speed of sound questions. Are you familiar with the trick where you can figure out how far away a lightning bolt is by literally timing between seeing the lightning bolt and hearing the thunder? Let's put some practical math to that. We're tracking a storm, we see a lightning bolt take place, and once we see it, we immediately begin a stopwatch and time out that it takes an additional 6.4 seconds for the thunder sound wave to reach us. That difference happens because light and sound travel at vastly different speeds. The speed of light is so fast that the human brain just perceives it as instant. The light would probably reach you in a few nanoseconds, if even that slow, and the human brain doesn't operate that fast. So light's functionally instantaneous for us. We don't have to bother calculating the time it takes the light to reach us. That would just be, some number of nano or picoseconds. So instead, we're just going to treat the light as instant and count the difference between the light hitting us and the sound hitting us. And we want to know the distance that the sound travels, which would tell us the distance between us and the lightning bolt that generated it. So we know time, we want distance. To do that, we need to know the speed of sound. Now that's usually 343, but this is a hot day. It's not 25 Celsius outside, it's 32. And if we're being good physicists, we need to take that into account. 32 Celsius. So the first thing we should do is adjust the speed of sound accordingly. And once we know that speed of sound, we can figure out how far it traveled in 6.4 seconds. We can assume sound travels at constant, whatever the speed of sound is in this temperature of day, we can just assume it's constant. Sound doesn't really accelerate unless the temperature suddenly changes or the pressure suddenly changes. We're going to ignore pressure for simplicity's sake. So formula number one, totally fine for just speed of sound, distance it travels per time. Same is true for light, it's just, too fast. But we don't need anything more special than this once we figure out the speed of sound. So, are we going to plug in 32? No, how many kelvins would that be?
305.
Thank you. If it's been a minute, just add 273 to a Celsius temperature to get its Kelvin equivalent. So that's 305 Kelvin. So 331 times the square root of 305 over 273. And that will give us an adjusted speed of sound of just shy of 350. And that will come out in meters per second because the 331 is in base units of meters per second. So faster on a hot day, and this will affect the answer slightly. This actually means that summer storms are further away than they might seem, since in summer the air is hotter, and that means the sound travels further in the same amount of time. So if the air is hot, that means the storm is further away than you might originally think. If the air is cold, it's closer. Be careful. Well, once we have that adjusted speed, we can figure out how far the sound has to travel in 6.4 seconds to reach our ear. And that should come out to about 2.2 kilometers. 2,200 odd meters. So you're probably pretty safe from this one. I'd only be worried if the sound reaches you in like 1 second or 0 seconds. But if it took 0 seconds, you probably got hit by the lightning and then you have other problems. Note again, if the speed was slower on like a cold day, it would have traveled less far in the same amount of time, which means it would be closer. So note whether the storm takes place in summer or winter. Any questions for this general application of the notion? All right. Before I move on, I like talking about lightning, so if you'll indulge me for a moment. The reason that lightning makes a noise at all is because of what lightning physically does when it occurs. If you stick around to 1510 next semester, you'll learn, that's the semester you'll learn about electricity, and lightning may come up with that. I like talking about the lightning, but you know, I just like physics. When lightning happens, electrons race out of the sky and into the ground or a tree or some poor golfer. And when those electrons pass through air, the air is suddenly energized and it flash turns into plasma, and that's why you can see it. It's still air, like what you see for lightning and electricity is just air energized and turning into plasma for a second, which is technically what's happening in these light bulbs too, and neon signs. That plasma is superheated, so it glows, and that's where the light comes from. And that's going to reach you as instantly as the human brain can process, so we don't really care about that amount of time. But the sound is different. What happens when the air turns into plasma for a second is it expands faster than the speed of sound. Like it goes from taking up this much room to taking up way too much room, way too fast. And that literally creates a pressure wave that we hear as sound, as a thunderclap. And so that is then what takes 6.4 seconds-ish to reach you. So, lightning is just plasma that exists for a second to make light and then make noise. And that's also why sometimes you can smell ions on a stormy day. Like sometimes I feel like I can smell ions in the air and I know it's going to thunderstorm later. Just because plasma is ions. All right, one more quick application of this. I want to kind of mention the caveat that echoes bring into tracking the speed of sound like this. We're going to do a similar thing. We are going to factor in the temperature of the air to figure out the speed of sound, except this day is freezing, and instead of looking at a lightning bolt, we are going to scream into a cave, because this is a different trick you can use. Sometimes in movies, or I guess even caving, someone might either scream into a cave to try to hear their echo and figure out how deep it is. You can do the same thing down into a hole. Different times what someone will do is they'll just drop something into the hole and wait how long to hear when the sound reaches them. So tricks like that you can figure out how deep a cave goes or how far down a pit goes. So we're going to do the same basic thing, factor in the temperature of figure out the speed of sound at 0 Celsius, and then figure out how far deep this cave goes. So, you scream into a cave, sound waves are going to come in, and then they're going to echo back out. And that process is going to take 2 seconds. Now on a freezing day, 0 Celsius is 273. So the speed of sound on a freezing day is just going to be that 331 on the front. And so, in 2 seconds, 331 meter per second sound can travel 662 meters. Is that the depth of the cave? No. Again, I'm bringing this up just to point out there's a caveat to echoes, because the echo took half of that time to travel from your mouth to the back of the cave, and then the other half to come back. So the sound did travel a total of 662 meters, but half of that was on the way in, half of that was on the way out. So the cave is only 331 meters deep. So if you're dealing with echoes, either you have to cut the time in half up front to find the distance the sound really traveled on its way in, or you have to remember, at some point you have to cut something in half. And echoes will at least show up on your homework once or twice. So, just a disclaimer when doing those problems.
So that's the length of the sound going forward and backward?
Correct. Because you only hear the echo once it bounces off the back and then comes back to you. It's kind of like, you know, if you run to the end of a football field and then run back, you ran the length twice. So just note if the problem says echo, because you do have to factor that in sometimes. Questions at this point? All right. There's one more sound-related concept we're going to cover this year, and it's got a weird formula to it, so at the very least we'll introduce it today and continue to practice it on Friday before we move towards exam territory. The last sound phenomenon we're going to cover is the Doppler effect, which technically is true of all waves, not just sound. Has anyone heard of this? At least the name Doppler before? Okay. Growing up, I heard it most often on like weather broadcasts, Doppler weather radar, and what they're describing is what we're about to talk about. Have you ever noticed how, like, when an ambulance is driving past you, the pitch of the sound changes as it passes, as it's approaching? It's got like a higher pitched whine, and then once it's going away, it deepens slightly. It doesn't even have to be like a siren. Sometimes just a car with no sound, with no siren attached, does something like this. I'm going to do an awful impression real quick. That shift that happens right as it passes you. That's a real thing. It's a real thing that happens. You're not just imagining things. And we call that phenomenon the Doppler effect. What's happening here is this, the frequency that you perceive changes if either the source of the sound is moving or if you are moving. If you think about what a siren is doing, it should always be making the same frequency of sound, right? It's just a physical device doing the same thing over and over again. Its pitch shouldn't just spontaneously change based on its location to you, right? The physical object isn't programmed to change what it's doing based on your location. The one object should make the same frequency over and over again. Same is true for just a car or a train passing. The physical object is moving at the same speed. It's got the same fundamental frequency. The object's not going to spontaneously start giving off different frequency sound waves. So something is causing the change as it passes you. And that change is ultimately due to the speed of the source of the object and whether it's moving closer to you or away from you. Where's my eraser? I'm going to hastily and very poorly draw a stationary human and a stationary ambulance. So right now nothing's moving.
This ambulance is parked. It's got the siren turned on. And let's say that siren is tuned to create 100 hertz sound, just for simplicity's sake. We've talked about how specific frequencies always have specific correlated wavelengths. So 100 hertz sound waves, every 100 hertz sound wave should have the same wavelength, right? That means that all of those waves should be the same distance apart. Every crest should come out the same distance from every following crest. So as long as nothing's moving, all of these waves should have the same wavelength, they should be the same distance apart. And that's true when you're standing still. If you are standing still, the ambulance is sitting still, same frequency, and nothing's moving, it's just the same constant pitch blasting you, right? The same's true for anything as long as you're sitting still. But something weird happens when the ambulance starts moving, and cars move fast enough for this effect to be noticeable. If the ambulance is moving towards you, it's still supposed to be making the same frequency of sound. Again, the device is set to the same frequency. That doesn't change. But when it's moving towards you, something kind of weird happens. Like, the sound is faster than the ambulance, so it's not like you can catch up to the sound waves you're making. If you can, you get a sonic boom, and an ambulance shouldn't be doing that. But when the ambulance starts moving, it's going to be closer to the wave it just made than it's supposed to be, right? If it's sitting still, one wave should be, the same 2 meters away before the next wave comes out, and that should be constant. But if the ambulance is moving, it'll be closer to the previous wave than it's supposed to be. So like, if the sound travels 2 meters in a nanosecond, the ambulance might be 1.75 meters away from it instead of the full 2. And that means that the next wave gets made closer to the previous one than it's supposed to. If the ambulance was staying still, the next wave would come out 2 meters away. But if the ambulance is slightly closer, the distance between the two waves shrinks. It's making the next wave closer to the previous one than it's supposed to. And that kind of has the effect of bunching the waves up together. The device is still designed to make the same frequency of sound, but the waves are being made closer to each other than they're supposed to. Kind of like if you have an assembly line that's making cookies or something, and the dough is meant to get extruded at a specific speed. Like, the machine plops out a cookie, and then the conveyor belt moves on past underneath it. If you crank up the speed of the conveyor belt, the cookies are going to end up getting smushed together because the belt is moving too fast, the timing is off. And then if you slow the belt down, the cookies end up blotted outwards. They end up, wider than they're supposed to. That's again because of the speed of what's making them. The next wave gets made closer to the first one than it's supposed to, and that bunches the waves up together. It might not literally cut the wavelength in half, but it at least makes the wavelength smaller. And a smaller wavelength correlates to a higher frequency, like we calculated earlier. We got lower wavelengths for higher frequencies of sound. So when something's moving towards you, that very act drives up the frequency of sound that it's making, even if the physical device isn't doing anything different. And that's why the ambulance has a higher pitched whine as it's moving towards you. And then the inverse happens as it's moving away. I'll just show that real quick. If the ambulance is moving away from you, it is now further away from the last sound wave that it made, and that draws the wavelength out. And bigger wavelength means lower frequency. So once it passes you, it suddenly switches from high pitch to low, and you can hear the meow. that phenomenon is the Doppler effect. And we'll do math for it on Friday. Basically, it's just changing the frequency you hear based on your speed versus the speed of the source. And it gets brought up on the news sometimes because we use it. Basically, this is the principle that all speed detection radar is based on. We'll talk about the math for that on Friday. Any questions for right now? Yes, there is lab this week. It's the last one. You know, you guys need anything? Anything at all? Have a wonderful day. Pay attention to any cars passing. See if you pick up on this.